Hello students, myself Dr. Sofia Gupta. So in this video we'll cover the topic potential energy surfaces for H3, H2F and HCN molecule. Before starting the topic, you should know about the degrees of freedom. Degrees of freedom. The meaning of degrees of freedom means in how many possible ways an atom can move in a space. So total number of this I am writing DOF, total number of degrees of freedom, we have 3n, where n is the total number of atoms in a molecule. Like for example, if you are having carbon dioxide, so carbon dioxide total number of atoms are 3, so the degrees of freedom will be 3 into 3 9. So carbon dioxide will be having total 3n degrees of freedom, right? Then now degrees of freedom are of three types: translational degree of freedom, rotational degree of freedom, and vibrational degree of freedom. Okay, so we know that translational degree of freedom means the molecule can move in a straight line. Like the molecule have three options: either it can move along x-axis or along y-axis or along z-axis. So the total translational degree of freedom is 3. Molecule can move in any of these axes. Then is rotational degree of freedom. Here we take two categories, for the linear molecule and for the non-linear molecule, right? For the linear molecule, see, these are the axes x, y and z. Linear molecules are those molecules which are linear in nature, in a straight line. For example, if the molecule is on x-axis, then it will have only two options available, that is it can rotate either along the y-axis or along the z-axis. So for the linear, the total degree of freedom is 2. Now if the molecule is non-linear, matlab the molecule is not on the straight line, if the molecule is like this, so it will have all the three axes available. So the total non-linear rotational motion is 3. Now we know that this is a vibrational degree of freedom. It can also be divided into linear and for the non-linear molecule. Clear? Now we know that total there are 3n degrees of freedom, out of which 3 are translation, 2 linear rotational, 2 non-linear rotational. So how much left we can separate from total translation and linear? 3 plus 2 5. So this will be the total vibrational degree of freedom. For a non-linear molecule, similar sense, total minus translation 3 plus 3 6. So this is the non-linear degree of freedom. I hope that is clear. Let's understand with the help of an example. For example, you are having carbon dioxide molecule. Okay, we all know that it is linear in nature, as carbon in this is sp hybridized. Okay, so in this the total degree of freedom will be, we know 3n, so 3 into 3 9, out of which 3 will be translational. Okay, for the rotation, I have told you it's a linear molecule, so rotation is fixed. So vibrational degree of freedom is 3n minus, see, for the linear it was 3n minus 5. Okay, so 3 into 3 minus 9 minus 5, 4 will be the vibration. You can also do like total it was 9 minus translational 3 plus rotational 2. So 9 minus 5 is equal to 4. Okay, I hope this is clear. Now the next is we'll discuss about Morse potential energy diagram. Energy diagram. Okay, Morse potential energy diagram. Basically, it is a diagram between the diatomic system. Now, diatomic systems are those systems which are having two atoms. So let's consider A and B atom. In the Morse potential energy diagram, we are having potential energy along the x-axis and the internuclear distance along the y-axis, right? In this, what you have to consider is that the position of the atom A is fixed and the atom B is moving towards the atom A. Like A is fixed and B is moving towards the atom A. Now, as the atom B moves towards the atom A, we know that the force of attraction will start and bond formation will take place. Okay, now due to the formation of bond, the energy will be released. Always remember, when a bond is formed between two atoms, then always there is release in energy. Okay, so the energy will release, so potential energy of the system will decrease. Now, up to a certain point, the potential energy of a system will decrease. This point indicates that the bond formation between A and B took place. Now, if further I move B atom further close to A, then the repulsive forces between the electrons will dominate. So the potential energy of the system will increase after this point. So here the potential energy of the system will increase. So this point indicates the point where the bond is formed between A and B. Okay, so this is also known as equilibrium bond length. So this is the equilibrium point where the bond formation take place. If I move from this point, if I move more close B to A, then the repulsive forces between the electrons of A and electrons of B will start, and this system will become unstable, so the potential energy will rise drastically. I hope this is clear. Okay, now we'll come to a topic. Now we'll see a topic, PES graph for H3 system. Okay, see, in the previous we were having a two diatomic system, right? So this was AB was a diatomic system. For a linear it was 3n minus 5, so 3n minus, this is a 1. Basically, in the whole scene we will consider vibrational degrees of freedom, because in a chemical bond always vibrational factor dominates over translation and rotation. So in whole of further diagrams we will only consider the vibrational degrees of freedom. Okay, so in this the one was a vibrational degree of freedom. So we have plotted potential energy against the one coordinate. Understand this point very carefully, that we have here one vibrational degree of freedom. So we have plotted potential energy against one reaction coordinate, right? Now in H3 system, let's say we have three atoms, HA, HB and HC. These all atoms are same, just I have represented this differently, ABC all are H atom. Okay, so now this we are having 3 hydrogen atom. We know the vibrational degrees of freedom is 3n minus 6 for the non-linear system. That was in a previous example, it was a diatomic system, so it is always in linear geometry. Here we don't know whether it will be linear or non-linear, so we have considered it as a non-linear molecule. Okay, so vibrational degree will come 9 minus 6 4 3, sorry, 9 minus 6 is 3. So the vibrational degree of freedom is 3. Now there we were having 1 degree of freedom. So we got this graph. This is a 2-dimensional graph, right? Now for 1 degree of freedom, we got 2-dimensional graph. If we are having 3 degree of freedom, we will get 4-dimensional graph. Okay, because here there will be 3 reaction coordinates. That is, the potential energy of the system will be the function of 3 coordinates. That you can write like this. Potential energy is a function of 3 spatial coordinates. In the previously, potential energy was a function of only 1 spatial coordinate. Here it's a function of 3 spatial coordinates. What are these 3 spatial coordinates? First is the atomic distance between HA and HB. Second one is the distance of HC from the midpoint of HA and HB. The distance of HC from the midpoint of HA and HB. Third is the angle which the HC made from the midpoint of HA and HB. Okay, so this is angle, this is HA, HB, and this is the angle that HC makes, right? Now we know that it is a function of 3 spatial coordinates. Okay, and for the 3 coordinates we'll get a 4-dimensional graph. Now it is not possible to draw a 4-dimensional graph, so out of these 3 we will consider 1 coordinate as constant. So we will consider that the angle with which HC approaches AB and HB, HA and HB is 180 degree. That is, HC is approaching like this. HC is approaching in a collinear manner. I hope that is clear. Okay, so now we are left, this we have assumed, so we are left with 2 spatial coordinates. Now we have 2 coordinates, so now we'll get 3-dimensional graph. For 1 coordinate we were getting 2-dimensional, for 3 we are getting 4-dimensional. Out of 3 coordinates we have just fixed out 1 coordinate, and for the 2 coordinate we are getting 3-dimensional graph. So now let's draw this 3-dimensional graph. Okay, for drawing the 3-dimensional graph, we know that it will be potential energy versus 2 coordinates. So the first coordinate is HA HB distance, and the second coordinate is HB HC distance. Okay, this we represented as R AB, this is R BC. See, in the third we have assumed that HC comes in a collinear manner. Okay, so we have considered this in the second coordinate. Now we will draw the 3-dimensional graph. See, firstly you have to draw the 3 axes, that is x, y and z axis. Now see here, in the both coordinates HB is common, so we will fix the point B over here, and A will be moving towards B from the x-axis, and C will be moving towards B from the this z-axis. So this will be basically RAB, and this will be, see this one, this will be RAB, and this will be RBC. Okay. See, for the two dimensional, it was, the graph was like this. Now we will combine both the graphs, like this is a combination of two graphs, so the diagram will come like this. So this is the diagram. Here we are having potential energy, here are AB, and here are BC. This is basically the combination of two graphs. You can see it clearly. As A approaches B, the potential energy decreases up to a point. So this point is known as RAB, where the bond formation take place. And further, if we move above, then the potential energy of the system increases. Similarly, as the C moves towards B, the potential energy decreases. At this point, the bond formation takes place. So this point is RBC. Now further, if I make the atom C moves close towards B, then the potential energy increases. So this is basically the combination of two points. Okay. So this was the potential energy diagram for the HC system. Now if I want to draw the same diagram in a three-dimensional form, so this was basically the diagram in 2D. If I want to draw the same diagram in the 3D form, you can draw like this. You can make a cube. Now I am representing the same diagram in the 3D figure. Okay, so here it was potential energy, so this is a potential energy, right? Here was an atom B, so we'll place an atom B over here. Then here, from here A is coming, so this is RAB. From here C is coming, so this is RBC. Same diagram will draw over here. So this basically, this is the potential energy diagram in the 3D form, and this is the potential energy diagram in the 2D form. I hope that is clear. Okay, then next is contour maps. Okay, contour map. Now see, now contour map is that if I cut this three-dimensional figure into slices like this, and this, if I cut this into the slices and take a slice of it, it will represent the change of potential energy with the reaction coordinates. So in order to draw a contour map, you have to follow the steps like in the previous figure. Let me copy paste over there. So this was a 3D figure. Now in order to draw contour map, what you have to do, you have to make a square. Okay, so this point B will come over here, so mark the point B over here. Now side of B was A, and so A will come here. This side of B was C, so C will come over here. So A will come over here and C will come over here. This will be RAB and this will be RBC. Okay, now at a point B there was this dip, so we will draw like this at a point B, right? Now at a point A This point represents the form of the dip in the potential energy. So here we will represent the dip in the potential energy, right? Similarly, at a point BC, at this line, this was a dip. So here we will show the dip. Now this will be your contour diagram. This is basically a 3D diagram. If we take a slice of it and this I'm cutting it and seeing from the top, then the diagram will come like this. Now in this diagram you have to note down 3 points. First is you have to make the trajectory. First is directly joining these points. Second trajectory is this L shape. Third is above that. So mark this A, this is B, and this is C. I will discuss one by one. For the trajectory A, so what does the trajectory A represent? It represents firstly the HA molecule was very far away from HB and HC molecule. These two are connected. HA was not connected to this. It was very far away, but slowly HA will approach. So the distance between HA and HB decreases while the distance between HB and HC increases. Finally, what happens? There is a formation of bond between HA and HB, and HC will separate out. So this is a trajectory A. Second was the trajectory B. So in this, what happens? The distance between HA and HB, the distance between HA and HB and the distance between HB and HC, they changes in a similar fashion. Means how much close HA will come to HB, that much far HC will go out of HB. So finally the bond formation will take place. Okay. Third was the trajectory C. In this, basically HA moves towards HB slowly, and slowly the HC is moving out. So finally a bond is formed between HA and HB. HC is out. So basically in 3 trajectories, the motion of HA towards HB, that is their distance varies, but the phenomena that is happening is same. That is, first HA was far away from HB HC, and gradually after certain steps there is a bond formation between HA and HB, and HC will get separated out. I hope that is clear. So this was for the H3 system. Now we will apply the same concept to the second system, that is FH2 system. In this, basically in the H3 system we were having 3H. In this system we have replaced one of the H with F. So one of the H with the F. So this is your system. Now in this we know that the trajectory that would be followed is A trajectory, because fluorine is more electronegative and it will easily form a bond between HA, and HB will leave out. So the contour map for this is just the L trajectory, A trajectory, sorry, it is an A trajectory. So this will be your contour map for the C. Okay. Like if the question comes for this system, so basically you have to full explain. If it is coming in 8 marks, then you have to explain the H3 system. Then you can write a line that in this basically the trajectory A is followed. So this will be your contour diagram. Now for the third system, HCN system, this is also a 3 atom system, but in this all the 3 atoms are different. So H moves towards CN, and here no atom will move apart. Instead HCN molecule as a whole is formed. So its contour diagram is HCN, RCN, like this, and then you have to draw 3 circles. This is a three-dimensional diagram of the HCN system. Students, I hope the complete lecture is clear to you. If you are having any doubt, kindly pin down in the comments.